Welcome to the deep dive. Today, we're looking right at you.
Yeah, directly at you.
Whether you are a developer prepping to architect your next big project, an entrepreneur thinking about rolling out digital loyalty points, or just someone insanely curious about how crypto actually works under the hood.
We are getting into the foundational layers of how this technology operates.
Exactly. We're pulling from Module 3 of the Vibe Code blockchain course notes today.
Yeah.
And the mission for this deep dive is to demystify exactly how you can issue custom tokens on the Stellar network.
Which is a fascinating process.
It really is. Because the big differentiator here and what makes this so worth analyzing is that doing this requires zero smart contracts.
Not at all.
Right. So we're going to explore the architecture, the operational security models outlined in the notes, and just give you those crucial aha moments without bogging you down in overwhelming info overload.
It's all about getting that clear picture at the protocol level.
Okay, let's unpack this. Because to really appreciate the architectural shift Stellar represents, we kind of need to look at the established paradigm first, right? Like creating tokens on networks like Ethereum.
Right. The contrast with Ethereum is what makes this so illuminating. On a Turing-complete network, token issuance is an inherently developer-heavy process.
You're writing custom code.
Exactly. You are writing custom Solidity code to deploy an ERC20 smart contract. And that contract is essentially a standalone database living on the blockchain.
Keeping its own internal ledger of who owns what.
Yeah. But because you are introducing custom logic, you introduce massive security overhead. You need extensive code audits to prevent vulnerabilities like reentrancy attacks.
Which are a nightmare. And then you pay significant gas fees just to deploy that contract to the main tree.
Right. Stellar approaches this entirely differently. Token issuance isn't an add-on or a piece of custom third-party software.
It's built right in.
It is a primitive operation built natively into Layer 1. The protocol itself handles the ledger state.
Meaning anyone can issue an asset natively in minutes.
With zero code, without writing or auditing a single line of smart contract code.
That structural difference removes a tremendous amount of friction,
Mm-hmm.
but it immediately raises a security question for me.
Go on.
If the barrier to entry is just executing a native protocol operation, and you don't have a unique contract address to point to, how does the network handle asset identity?
Ah, right.
Because the impersonation vector in crypto is massive. I mean, I could theoretically mint a token right now, name it USD, and try to pass it off as official fiat collateral.
Well, asset identity on Stellar is managed through a bipartite system. Every single asset requires two distinct pieces of information to be recognized by the network.
Okay, what's the first one?
First, you have the asset code. That's a 1 to 12 character alphanumeric string. You could name your token MY token, AFRI, or indeed USD.
But strings are easily duplicated.
Exactly. Which is why the protocol mandates a second component, the issuer public key.
So the cryptographic address of the specific account that created the asset.
Precisely. To use the example from the course notes, consider USDC. Circle, the financial institution, issues the official USDC stablecoin.
Right.
Their USDC is fundamentally distinguished from a token named USDC issued by an arbitrary user. They might share the exact same asset code, but because the issuer public keys are different, the Stellar protocol treats them as entirely separate assets.
So they don't share order books or anything.
No, they cannot be conflated in a payment operation. The network elegantly prevents naming collisions right at the base layer.
That handles the impersonation problem by hardwiring the issuer's identity into the token itself. It basically shifts the burden of trust from reading a complex smart contract to just verifying a single public key.
Yes, which is much simpler for end users.
But minting the token is just the initial operation. Managing the lifecycle of that token introduces significant operational risk.
It does.
The notes heavily emphasize what they call the three-account architecture. If you're issuing an enterprise-grade asset, the standard practice is to partition your operations.
Right, across an issuing account, a distribution account, and the eventual user accounts.
Let's break those down. The issuing account acts as the cold wallet. It mints the tokens, and its public key serves as that definitive identity marker we just talked about.
What's fascinating here is the concept of the blast radius.
The blast radius.
By isolating the issuing account from daily operations, you are mathematically limiting potential damage. Your issuing account should ideally be generated and stored in a completely offline environment.
Like an air-gapped machine or an encrypted USB.
Yes, or a highly secured hardware module. It serves one singular, highly restricted purpose. It signs the transaction that mints new tokens and sends them to your distribution account.
And the distribution account, conversely, operates as your hot wallet.
Correct.
Now, keeping the issuer key air-gapped is standard security hygiene. But the operational friction of moving funds from cold to hot storage can be a nightmare for high-volume ecosystems.
It can be challenging, yes.
If you are running a retail app handling thousands of microtransactions, your distribution account is constantly active, sending tokens to end users all day. Does this architecture realistically hold up under that kind of daily operational stress?
It does because of where the risk is concentrated. The distribution account is inherently vulnerable because it has to be online to process customer withdrawals or loyalty rewards automatically.
Right, it's exposed.
But if that hot wallet is compromised by a malicious actor, the damage is strictly contained to the undistributed float sitting in that specific account.
So they can only steal what's in the hot wallet.
Exactly. The attacker can drain whatever tokens are currently in the distribution account, but they cannot mint new ones.
Because the issuer key is offline.
The crucial issuer key, the key that controls the total overarching supply of your token, remains perfectly safe. This isolation is why the course notes highlight this as the standard architecture for serious network participants like StellarX and USDC.
So you essentially compartmentalize the catastrophic risk. Losing the hot wallet is an operational setback. Losing the issuer key is the death of the asset.
Well said.
That brings us to the third component of the architecture, the user accounts. On many other networks, a massive pain point is wallet spam.
Oh, absolutely.
Anyone can airdrop a malicious or worthless token into your wallet without your consent, cluttering your interface, creating tax liabilities, or even acting as phishing vectors. Stellar handles this entirely differently, right? With trustlines.
Yes, a trust line is a mandatory explicit opt-in mechanism. It is a cryptographic handshake where a user submits a change trust operation to the network.
Basically saying, I trust this specific asset code from this specific issuer public key.
And I consent to hold it. Without that operation, a user's account simply cannot receive the custom asset.
So if an attacker attempts to send you 1 million newly minted unsolicited tokens,
The protocol will automatically reject the transaction at layer 1.
that acts as a phenomenal anti-spam shield. But looking at the implementation details in the notes, establishing that trust line isn't entirely free.
No, it requires a reserve.
When a user runs the change trust operation, it locks a reserve of 0.5 XLM Stellar's native Lumen token in their wallet. Now, locking 0.5 XLM per trust line sounds trivial for a single user.
It's a very small amount.
But if you're building a retail application and onboarding 100,000 users, that is 50,000 XLM locked up just in network reserves. Does the protocol offer a way to manage that friction?
It does. First, it's important to understand the reserve is a necessary anti-denial of service mechanism. It ensures the global ledger isn't bloated by millions of empty trust lines.
Right, it prevents spamming the network itself.
Exactly. However, that 0.5 XLM isn't burned or lost. It is strictly a locked state. If the user ever decides they no longer want to hold the asset, they can execute the change trust operation again.
Setting their trust limit to 0.
Yes, which removes the trust line and immediately unlocks their XLM. And to your point about onboarding friction, developers often utilize channel accounts.
Or sponsor the initial wallet funding, as Nathan's mentioned.
Exactly. During the onboarding flow, they can abstract this reserve requirement entirely away from the end user.
It's a smart trade-off between ledger bloat and user friction. Speaking of the trust limit, the notes specify a highly specific standard practice. When setting up an uncapped trust line, developers are advised to use the limit parameter 9223337203685.4775A07.
It looks like a random string of numbers at first glance.
It really does. Why that specific number?
It is actually a very specific architectural constraint. That number is the maximum value of a 64-bit signed integer. Because the Stellar network calculates balances using an integer representation of stroops, where one stroop is 1/10,000,000th of a unit.
Got it.
So the maximum possible representable number divided by 10 to the 7th power gives you exactly 922,337,203,685.4775807.
So by passing that specific maximum integer as the limit, you're effectively telling the protocol that the trust line is uncapped up to the mathematical limit of the ledger.
Exactly. It's a clever use of the system's own constraints.
That is the exact kind of protocol-level detail that separates a surface-level understanding from actual technical competence. So we have the theoretical defense system of the three accounts and the mathematical constraints of the trust lines. But putting it into practice requires a specific sequence of operations.
Yes, order of operations matters greatly here.
The source notes walk through the actual life cycle of getting a token into circulation using Node.js vibe coding prompts. Essentially, using conversational AI to generate the Stellar SDK boilerplate. First, you generate your issuing and distribution key pairs. On the testnet, you fund them using FriendBot, which acts as the network's developer faucet.
And once the accounts exist on the ledger, the sequence is strictly enforced. Before any minting can occur, the distribution account itself must establish a trust line to the issuing account.
Even though you own both accounts.
The protocol does not grant exceptions to your own accounts. The rules of asset consent apply uniformly across the entire network.
Then comes the minting operation itself, which is surprisingly lightweight. There is no complex minting function to call.
It is simply the issuer account creating a standard payment operation.
Sending the specified amount of the new custom asset to the distribution account.
Exactly. Because the asset didn't exist in the distribution account's balance beforehand, that payment operation from the ultimate authority, the issuer, is what actually brings the tokens into circulating supply.
From there, the distribution account executes a distribute tokens function to disperse the asset to the actual end users.
Provided those users have already broadcast their own change trust operations.
Right. And all of these state changes can be verified on block explorers like Stellar Expert. You query the asset code and the issuer public key, and you can audit the total circulating supply, the active trust lines, the transaction history.
It's completely transparent.
To ground this in a practical architecture, the course notes provide the Brewcoin use case, BROW.
A great example.
A local coffee shop rolling out a digital loyalty point system. Instead of maintaining a centralized database of punch cards, they deploy Brew tokens on Stellar. The business logic dictates that for every 10 Rand a customer spends, they are allocated one Brewer token.
The lifecycle maps perfectly to what we just discussed. The customer downloads a wallet, which abstracts the process of creating a trust line for Brew.
When they make a fiat purchase, the shop's backend triggers the distribution account to send one Brew to the customer's public key.
The customer accumulates these tokens natively on the ledger, and eventually they initiate a payment operation back to the shop's receiver account to redeem them for physical goods.
Like free drinks. And because it's on a public ledger, the customer actually custodies their loyalty points, rather than just trusting an entry in a corporate database that could be wiped out tomorrow.
It grants true ownership of the asset.
The notes point out this same primitive applies whether you are denominating a local neighborhood currency or going much larger and tokenizing real-world assets. They detail a prop token scenario where a property firm issues an asset where one token mathematically represents a 1/1000th fractional share of a physical commercial building.
The tokenization of real-world assets is a primary use case, but the utility of these assets relies heavily on liquidity.
Here's where it gets really interesting. Once prop token or Brewcoin or any custom asset is minted, it does not exist in isolation, because Stellar features a built-in decentralized exchange, or DX, native to Layer 1.
Every custom token shares the same global order book protocol.
You're not relying on fragmented liquidity pools across different third-party smart contracts like on Ethereum. And you don't have to petition a centralized exchange to list your asset or pay exorbitant listing fees.
The moment the token exists, you can broadcast a managed sell offer operation.
The notes even show how to prompt a script to place 100 of your tokens on the testnet DX for 1 XLM each.
Because the DX is integrated into the base layer, it enables an operational feature that fundamentally disrupts traditional foreign exchange markets: path payments.
Path payments are incredible.
A path payment allows a user to initiate a transaction sending one type of asset, while the protocol dynamically ensures the receiver is credited in a completely different asset.
And the conversion is handled atomically in the background by routing through the native order books. Let me clarify the mechanics of that for a second.
Please do.
If I need to settle an invoice with a vendor in Europe, but I only hold tokenized US dollars, and they only accept tokenized euros, I don't have to manually trade USD for euros on an exchange, incur slippage, withdraw the euros, and then send a separate payment transaction.
Exactly the opposite. You initiate a single path payment operation sending your tokenized USD.
Within that same ledger sequence.
Yes, the Stellar protocol evaluates the global DX, identifies the most efficient conversion path, which might involve routing your USD into XLM, and then XLM into EUR locks the exchange rate and delivers the tokenized EUR to the receiver.
What happens if the market shifts in that split second?
If the path cannot satisfy the parameters, the entire transaction fails atomically. This protects the user from partial execution or unexpected slippage.
So it either goes through perfectly at the agreed rate or it doesn't happen at all.
Exactly. This automated multi-hop routing is the technological engine behind the massive cross-border remittance corridors mentioned in the text, such as AfriToken and EuroAnchor.
It functions as a universal atomic translator for value transfer. Now, an open permissionless DX is incredibly powerful, but the notes make it explicitly clear that Stellar is engineered to bridge the gap between trustless DeFi and regulated TradFi.
That bridging is crucial.
If you are issuing prop token, representing actual commercial real estate, you cannot have a wild, unregulated secondary market where anonymous wallets are trading unregistered securities.
If we connect this to the bigger picture, this tension between open ledgers and regulatory compliance is resolved through asset flags.
Asset flags.
When an issuer configures their account, they can utilize a set options operation to toggle specific granular controls. These dictate exactly how their token functions on the network. For highly regulated assets, the issuer would enable the auth-required flag.
Which means what, exactly?
This mandates that even if a user establishes a trust line, that trust line remains inactive until the issuer explicitly signs a transaction approving it.
So that immediately solves the compliance bottleneck for securities. You run your standard off-chain KYC and AML checks. Know your customer.
Precisely.
Once the user passes those background checks, your backend approves their trust line on-chain, and only then can they receive or trade the token.
Building on that compliance framework, there is the auth revocable flag.
Revocable.
This grants the issuer the protocol-level authority to freeze individual trust lines, immediately halting that specific account's ability to transact with the asset.
So they can lock a user out.
Yes. This is an absolute requirement for responding to international sanctions, freezing stolen funds, or complying with court orders. The notes specifically highlight that Circle utilizes this exact flag for USDC to maintain regulatory parity with the traditional banking system.
Makes sense.
There is also the claw back-enabled flag. This gives the issuer the ability to systematically burn tokens from a holder's wallet.
Wow, just reach in and take them.
Yes, which is often legally necessitated to reverse fraudulent transactions in regulated jurisdictions.
From a purely cryptographic purist perspective, giving an issuer the power to freeze or claw back assets sounds highly centralized.
It does.
But from an enterprise perspective, it's the only way a tokenized real-world asset can legally exist. You can't tokenize a building and not have a way to recover stolen equity.
Exactly. But on the flip side, if you are building a purely decentralized protocol and want to mathematically guarantee to your users that you will never alter the rules, you can invoke the auth-immutable flag.
So you lock it down.
Once that flag is set, the configuration is permanently locked at the protocol level. The issuer physically cannot change the authorization requirements ever again.
It really demonstrates the flexibility of the architecture. You can deploy a completely permissionless, trustless token or a highly permissioned, rigorously controlled enterprise security utilizing the exact same underlying layer 1 primitives.
It's all just toggles on the account.
Which naturally leads us to the ultimate security mechanism for token issuers permanently capping the total supply. Let's look back at the prop token scenario.
The real estate token.
Right. You mint the initial supply of 1 million tokens, representing 100% of the commercial building's equity. Your investors need absolute cryptographic assurance that you aren't going to turn the printer back on tomorrow, mint another million tokens, and dilute their equity by 50%.
A very real concern in TradFi.
To prove the supply is finite, the issuer returns to the set options operation and modifies an account property called master weight,
setting its value to 0. Adjusting the master weight to 0 on the issuing account is a terminal operation. In the Stellar protocol, every account has a weight threshold required to authorize transactions. By reducing the master key's weight to 0, you are permanently stripping that account of its ability to sign any future operations.
And the source notes place a massive warning label on this concept. It is strictly irreversible. Once that weight hits 0, the issuing account is permanently bricked.
Completely useless for future signatures.
No further tokens can ever be minted for that specific combination of asset code and issuer key. It mathematically locks the circulating supply, ensuring the token's scarcity and preserving its market value.
But the operational risk is immense.
Because if a developer accidentally executes that set options operation before minting the initial supply to the distribution account,
the asset is dead on arrival. You cannot reverse it.
It's the cryptographic equivalent of destroying the mold after a sculpture is cast. You trade operational control for absolute, verifiable trust.
It broadcasts to every participant on the ledger that the economic parameters of the asset are now immutable.
So what does this all mean for you? It means the infrastructure required to deploy functional enterprise-grade digital assets has been abstracted down to native protocol operations.
The complexity is gone.
Issuing custom stablecoins, fractionalizing real estate, or deploying automated loyalty ecosystems no longer demands deploying risky smart contracts or hiring specialized solidity auditing firms.
By implementing the three-account architecture, isolating the cold issuer key from the hot distribution key, and leveraging built-in parameters like network trust lines, native order books, and granular asset flags, developers can launch secure assets directly on the Stellar base layer.
The friction has been fundamentally removed.
It has. But this raises an important question regarding the future of tokenization.
Well, that's so.
Well, we have just analyzed how incredibly efficient and mathematically secure it is to issue an on-chain token that represents a real-world asset. The protocol flawlessly manages the trust requirements, the supply mechanics, and the native DEX liquidity.
It's technically brilliant.
But while the on-chain issuance is near perfect, it highlights the vulnerability of the Oracle problem. If deploying the cryptographic representation of a commercial building or a reserve of fiat currency, is this easy?
How do we prove it's real?
Exactly. How do we, as a network of participants, solve the off-chain problem of verifying that the physical building or the actual dollars in the bank account backing that token truly exist in the real world?